When some external load F acts on a beam, the shear force and bending moments are set up at all sections of the beam. If we consider a cross-section of a beam, the shear force acts parallel to the section, and the force due to bending acts perpendicular to the section. If we consider neutral axis at the center of the cross-section, then the upper fibers of the section goes into the compression and lower fiber goes into the tension due to bending. So mainly there are two types of stresses acts in a beam subjected to the force F, which are shear stress and bending stress. Shear stress can be calculated as shear force divided by the cross-sectional area A. So F divided by A. If B is the width and H is the height of the cross-section, then F divided by B into H. Coming to the bending stress, we can calculate the bending stress considering small length of dx of a beam. Consider a small length dx of this part of beam. Consider two sections AB and CD, which are normal to the axis of he beam NN. Due to the action of the bending moment, the part of length dx will be deformed. The top layer, such as AC, has deformed to the shape A-C-. It is clear that some of the layers have been shortened, while some of them are elongated. At a level between the top and bottom of the beam, there will be a layer which is neither shortened nor elongated. This layer is known as neutral layer or neutral surface, N-N-. This theory of bending is known as theory of simple bending. It is clear that top layers goes into compression and bottom layers goes into tension. A small length dx of a beam subjected to a simple bending. Due to the action of bending, the part of length dx will be deformed. Let A-B- and C-D- meet at O. R is the radius of neutral layer, N-N-, and theta is the angle subtended at O by A-B- and C-D'. Consider a layer EF at a distance y below the neutral layer NN. After bending, this layer will be elongated to E-F'. Original length of layer EF equals dx. Also length of neutral layer NN equals dx. After bending, the length of neutral layer N-N- will remain unchanged, but the length of layer E-F' will increase. N-N- equals N, N equals D, X N-N- equals R, multiplied by theta, E-F' equals R, plus Y multiplied by theta. But N-N- equals N equals dx, hence dx equals R multiplied by theta. Increase in length of layer, EF equals E-F- minus EF equals R plus Y multiplied by theta minus R multiplied by theta equals Y multiplied by theta. Now strain epsilon in layer EF equals increase in length, divided by original length equals Y into theta, divided by EF equals Y into theta divided by R into theta equals Y divided by R. Epsilon equals Y divided by R. Now the stress can be written as stress sigma equals strain, multiplied by Young's modulus equals Y divided by R into E. Sigma divided by Y equals Young's modulus E divided by R. Consider small section of length dy at a distance of y from neutral axis. Let dA equals area of layer force on layer equals stress multiplied by area of layer equals sigma, multiplied by dA equals E divided by R into Y multiplied by D. Total force on beam section equals E divided by R integration of Y dA. Integration of YdA represents the moment of entire area of section. Total moment on beam section equals force times distance y equals E divided by R integration of YdA multiplied by y. Moment M equals E divided by R integration of y squared dA. Integration of y squared dA is known as moment of inertia I. M equals E divided by R multiplied by I. M divided by I equals E divided by R. M divided by I equals E divided by R equals sigma divided by Y. It is known as the bending equation. Let's take one example. Consider a hollow shaft supported at both ends by bearings. There is a belt drive at the center which is driven by motor. Load at the belt drive is around 80 newtons. Shaft external diameter is 40 millimeters and internal diameter is 20 millimeters. Length of the shaft is 4 meters. Calculate the stresses occurred in the shaft. Given data is external diameter equals 40 millimeters, internal diameter equals 20 millimeters, length of shaft equals 4,000 millimeters, point load at middle equals 80 newtons. First, we need to calculate maximum bending moment, which can be calculated considering simply supported beam at both ends. Bending moment M equal to W into L divided by 4, which is equals 80 into 4,000 divided by 4, which comes 8 into 10 raised to 4 Newton mm. Moment of inertia of hollow shaft can be given by pi by 4 into OD raised to 4 minus ID raised to 4, which comes around 11780 millimeter raised to 4. Considering bending equation, M divided by I equals E divided by R equals sigma divided by Y. Hence, bending stress sigma equals M multiplied by Y divided by I, which comes around 13.58 Newton per millimeter square. Shear stress tau equals shear force divided by cross-sectional area, which comes around 0.08 Newton per millimeter square. We can combine the bending stress and shear stress using different failure theories. Let me know in comments if you want to learn about failure theories. I will make a different video for that. Thank you for watching the video.